Welcome back, focused learners. I am absolutely thrilled to have you here for today's explainer. We're looking at a completely monumental breakthrough from a 2024 paper by Tian and colleagues that has quite literally rewired how we think about AI image generation. We are talking about visual autoregressive modeling, or VAR. For years, we've watched large language models like GPT get predictably smarter just by throwing more compute at them. But images? Well, images have stubbornly refused to follow those same clean scaling rules. But that ends today. The architecture we're about to explore finally brings GPT-style predictable scaling laws right into the world of visual generation. So get ready, because this is a massive paradigm shift. Okay, let's dive right into this. Here is our roadmap for today. First, we'll hit the generation order problem. Second, VAR's big solution, next scale prediction. Third, the multi-scale tokenizer. Fourth, exactly why next scale wins on efficiency. And finally, we'll look at scaling laws versus diffusion. All right, part one, the generation order problem. To really appreciate the genius of VAR, we first have to understand the incredibly frustrating bottleneck that plagued all those pre-2024 autoregressive attempts. We're talking about models like PixelRNN, PixelCNN, and even the original DALL-E 1. They tried to generate images using autoregression, which is the exact same fundamental math that powers ChatGPT. But there was a glaring issue. No matter how much compute they threw at them, they just couldn't reach the high-fidelity quality of diffusion models at a matched compute budget. They were inherently stuck. And the typewriter versus the painter's canvas metaphor brilliantly illustrates why. See, language models work like a typewriter. They read and write text in a one-dimensional line, token by token, word by word. Early image models tried to do the exact same thing. They forced a two-dimensional image grid into a one-dimensional raster order, basically scanning top left to bottom right. Imagine a painter trying to paint a masterpiece by completing the extreme top left pixel perfectly before having any clue what the center of the painting is going to look like. An early corner pixel has absolutely no idea what the image is eventually supposed to become. Images simply aren't books, and treating them like text created a massive structural blind spot. Which brings us to part two, VAR and next scale prediction. The researchers behind VAR realized something crucial. To fix that generation order problem, they didn't just need to tweak the model. They needed to completely overhaul what was actually being predicted. They stopped trying to predict the image across space and started predicting it across scale. Let's walk through these exact steps, because it's almost like a cinematic focus bowl. Step one, the model predicts a single one-by-one token. This is the ultimate zoomed-out, blurry summary of the entire image. Step two, it uses that summary to predict a 2x2 grid of coarse features. Step three, that 2x2 grid conditions the prediction of a 4x4 grid. And this process just doubles in resolution at each step until we reach step K, generating the final high-resolution grid. Each scale directly conditions on the previous one, so it smoothly brings the image from a conceptual summary into razor-sharp focus. Predict coarser, then finer. That is the mantra here. It's the core philosophy of next-scale prediction. By generating the whole image at a specific scale in one single transformer pass, that terrible one-dimensional spatial order problem we talked about completely disappears. The model is no longer guessing what goes on the right side based on the left side. It's globally refining the entire image layer by layer. Moving into part three, the multi-scale tokenizer. So the crucial point is, how do we actually feed this process into a transformer? To peek under the hood here, we have to look at how the data is prepared. VAR needs what's called a multi-scale discrete tokenizer. It uses a codebook, which is basically a dictionary of visual building blocks, typically ranging from 4,096 to over 16,000 distinct visual words or tokens. And the secret sauce making this possible is residual VQ. Think of it as additive tokenization. The tokenizer produces those grids of increasing resolution we just walked through, but with a clever twist. Each scale is specifically trained to capture only what the previous scales missed. Again, it's just like painting. Your first layer is your broad strokes, and your next layer only adds the details missing from those broad strokes. The truly brilliant part? This tokenizer is trained once and then completely frozen. The decoder just takes the mathematical sum of all these scale embeddings to produce the final image. That leaves the autoregressive transformer to do all the heavy lifting of the actual prediction. Now let's look at the transformer's attention mechanics. First up, causal cross scales. This just means tokens use fixed positional attention to look back causally at previous scales. They're learning from the broader strokes. But look at that second concept, parallel within scale. This is huge. All tokens of the current scale are generated at the exact same time without waiting on each other. And to keep track of it all, the model uses a unique scale position embedding that logs a triple of the token scale, its row, and its column. All right, part 4, why next scale actually wins. This brings us to the payoff. We've seen the brilliant architectural math, but how does this translate to actual performance? Why does this specific structure absolutely crush older methods? Well, it comes down to some massive efficiency wins. First, going coarse-to-fine perfectly aligns with natural image statistics and, frankly, human vision. Our brains expect stable, low-frequency structures, like the general shape of a face, to dictate high-frequency details, like the pores on the skin. Second, parallel generation means we're generating in log scale length, not linear. And third, there is zero generation order bias. There are no artificial left of or above biases forcing the model into early blind commitments. This means you get way less hallucinatory weirdness in your generated images because the overall structure is conceptually locked in right from the start. 10. Because of that incredible log-scale parallel generation, for a standard 256 by 256 high-resolution image, VAR only needs roughly 10 transformer forward passes. That's it, just 10 steps to refine the image from a single dot all the way to full resolution. Contrast that immediately with the 28 to 50 forward passes typically required by diffusion transformers like DIT to achieve the exact same quality. 10 versus up to 50. This right here is the aha moment for why VR is profoundly faster at inference. It is mathematically skipping the tedious iterative steps that diffusion relies on. Finally, part 5, scaling laws versus diffusion. Let's bring this explainer home by looking at the macro impact of this 2024 research. I mean, the speed is great, but the true holy grail of AI architecture right now is reliable scaling. VAR finally brings the predictable text model power of GPT to images. VAR follows a predictable power law scaling curve for FID, which is the standard metric for image quality on the ImageNet dataset. If you double the parameters or double the compute, you reliably have the error. This was a completely historic moment. It's the first image generative model to exhibit scaling behavior as cleanly as language models do with Perplexity. For everyone tired of guessing if the new model will actually be better, this is a game changer. Future improvements won't rely on random, empirical architectural guesses. We can literally predict exactly how much better the model will get just by adding more compute. When we stack them up, diffusion and VAR actually share the same underlying data compression philosophy. They both break hard generation problems into a sequence of easier subproblems. Diffusion models gradually add noise and learn to undo it step by step. VAR models gradually add resolution and learn to predict the next scale. But when tested head-to-head on class-conditional ImageNet at matched parameter budgets, whether we're talking 33 million, 130 million, or 458 million parameters, VAR is just faster at inference and actually pulls ahead of DIT in quality. Which leaves us with this final, thrilling question. If VIR brings GPT-level predictable scaling to images, what happens when we perfectly fuse it with text? Researchers are already exploring this bleeding edge with models like HART, the hybrid autoregressive transformer, which introduces text conditioning directly to the VAR architecture. We are standing at the dawn of incredibly fast, perfectly scalable text-to-image generation that fundamentally understands visual structure the way a human painter does. Thank you so much for joining me on this Explainer Focus Learners. Keep exploring, keep questioning, and I'll catch you in the next one.